Hi, I'm Alistair, I'm a games designer, and in this video I'd like to teach you how you can create an electronic escape room puzzle that uses analog inputs and outputs, like this one. Let me show you how it works. Okay, so what we've got here is 4 sliding linear potentiometers, and at the top I've got 4 analog ammeter gauges. I've also got a handful of LEDs and there's a relay here, and that's going to turn on when the puzzle is solved. Now these are all wired on the back here to an Arduino Nano, and that's running the code that is powering the puzzle logic as well. So the idea is that when players encounter this in an escape room, what they might naturally try to do is fiddle with the inputs. So if they move this slide on the left up and down, we notice that the meter on the left also goes up and down. And if we move it to around the middle point, this LED comes on. Now, when LEDs turn on in escape room games, that's normally a good sign. So maybe let's try the second dial. And we notice it's the same again. We can move it up and down. It makes the second gauge go up and down. And now we've got the second LED lit as well. So now we're probably thinking this is pretty easy. We just move the third dial to the midpoint. But, oh, hang on. When we move it to the middle, the third gauge only goes up about a quarter of the way. And also the first one's gone off. We need to move it all the way to the top to get the third LED to light up. But now the first gauge is too high, so let's move that down or up or down or up, and hang on, that's not doing anything anymore. Oh heck. Okay, so we'll try the fourth slider instead, and that moves the fourth one, but oh crikey, now we've got the second, the third and the fourth are all moving. So, well, let's get that in the right position for the fourth one. Now we see that the third one is too high, so let's bring that one down a bit, and okay, well that's made the first one in the right position as well. Now if we look at the second meter, that now displays 0, so let's try sliding this up, and it goes up. Slide it down, it also goes up. So in fact we can move this either way, and when I get it right, listen to the relay in the corner here. So I'm going to slide all the way to the bottom. You see the relay clicks on, that will send power across the load side here, which could unlock a maglock, for example. Now there's actually a very simple set of rules that's controlling the movement of these dials, and I'll show you what those rules are when we look at the code a bit later on, and also explain how you can make your own rules up to customize the puzzle for yourself. If you like solving puzzles, you can try rewinding the video and seeing if you can work out what the set of rules are that I'm using at the moment. But what I'd like to do next is to talk in more detail about these analog inputs and outputs. Now, when we look at most escape room puzzles, and in fact electronic systems in general, we're used to using digital inputs and outputs. So those are ones that have a fixed set of values. A button, for example, is either pressed or it's not pressed. There's nothing in between. Or you might have a rotary switch that has one of a fixed number of positions. But what I've got here is a slider that has a completely continuous range of values. And likewise on the output side of things, the needle here can move smoothly from one extreme to the other. And it sort of has a nearly infinite amount of precision to it. I can move these, incrementally tiny amounts, and that's actually changing the value. But we also know that microprocessors like the Arduino don't really like thinking about numbers that have infinite precision. What they like working with is numbers that can be expressed as a fixed, exact amount. So in order to be able to do that in our code, what we're going to have to do is convert the analog inputs into a digital value first of all. Then we can operate them on our code as normal. And then at the end, we need to convert back again from digital to analog for the output. So to do that, we're going to make use of 2 features of the Arduino. Firstly, we're going to use the Analog-to-Digital Converter, or ADC. That's going to take our analog input and convert it into a digital value. And then at the end, we're going to take our digital value back into analog again using something called Pulse Width Modulation, or PWM. So let's take a look at both of those in more detail, starting with the input side of things. Okay, so here's one of the linear potentiometers I'm using. I should mention that you can also get rotary potentiometers like this one here. They basically provide exactly the same function, except you vary them by twisting this little knob on the top rather than by moving up and down a channel like this. But they work in the same way, and that's essentially to be a variable voltage divider. So inside this sort of channel here, there is a strip of conductive material, and you can see we've also got some pins on the side here. So we've got a ground, VCC, and an output pin. We've actually got two sets of them, but I'll come on to that in a moment. And what I want you to imagine is that the ground pin here is connected at one end of this conductive strip, and the voltage at the VCC pin, that's at the other end of the strip. And then the output voltage that you read on the output pin here is determined by the fraction of the distance that the slider is positioned, somewhere between all the way at ground, well that's going to give 0 volts, and all the way at the top, that's going to give whatever the value of VCC was. So for example, let's suppose that we supply 5 volts on the VCC pin, that's the operating voltage of most Arduinos. Ground is obviously 0 volts. If we then position the slider exactly in the middle, the voltage we would read at the output pin is going to be 2.5 volts, because that's exactly halfway between 0 and 5 volts. And if we move it lower down, it gets less. If we move it higher up, it gets higher, all the way between 0 and 5. Okay, that's great. That gives us a variable voltage. How do we then read that in our Arduino? Well, that's where we look at the analog-to-digital chip. So on an Arduino Uno here, you can see we've got a row of pins at the bottom that says analog in, and we've got 6 pins here on an Uno. If you're using a Nano, you've actually got 8 analog pins at the bottom here, and they're the ones prefixed with the letter A. And with any of those pins there, it's possible to take an analog reading of a voltage supplied to those pins and send it to the ADC chip that's on board the board here to convert it into a digital value instead. And the way that the ADC chip does that is it compares it to a reference voltage. That reference voltage we get at the AREF pin. So as I said, this is a 5 volt board, as most Arduinos are. In fact, this one is 5 volts as well. But you can also get 3.3 volt Arduinos, or you can actually supply an external voltage reference at the AREF source. And what will happen is the ADC will convert the voltage received on the analog pin here. It will compare it to that voltage on the AREF pin, and we'll convert it to a digital value with 10 bits of precision. So a 10-bit value, that can take anything from 0 to 1023. 10 bits means 1024 values, but one of them is 0 itself. So the highest value you can read is 1023, and that's where the voltage on the analog pin is exactly equal to the voltage on the AREF pin. Now, I should mention actually that although we've got 6 analog pins here, or we've got 8 on the Nano, there's still actually only one ADC channel on the board. And what happens when you take an analog reading of A0 or A1 or A5 or whatever, what you're effectively doing is you're kind of routing the pin there through the ADC chip in order to make a comparison to the AREF value. And what that means is that if you take a reading of several different analog pins kind of in quick succession, you can end up with a little bit of sort of contamination of your data, as it were, because you kind of very quickly route this voltage, then this voltage. They're all going through the ADC comparator chip one after another. So there's some issues there, but when I get to the code later on, I'll explain how you can deal with those to get a clean input signal here that you compare to AREF. So sort of working through a whole example from scratch then. So let's say we've got 0 at ground volt, we've got ground connected to ground, and we've got VCC connected to AREF, which on an Arduino Uno is 5 volts. And then we set our slider to halfway here. We are now getting 2.5 volts output on the output pin here, and we feed that into one of the analog ins. Then what we do is we take an analog read of the voltage on that pin. So we've got 2.5 volts here. We've got a ref of 5 volts. So that is half of the reference value. So what the ADC chip returns is half of the range of value between 0 and 1023. So it gives us the number 512. So when the slider is in this position, that is 512. It goes all the way down to 0 and all the way up to 1023. And everything in between, obviously. Now I did mention that there's actually 2 sets of pins here. We've got output A and we've also got output B. I believe the reason for this is that inside the strip here there's actually 2 sort of parallel conductive strips, and one of them feeds output A, the other feeds output B. And what you can do is you can take a reading from both of them. If you want a more reliable reading, you take a reading from both and average them, for example. Now I'm not actually doing that here. I am only connecting one set of these pins, but I am doing some other techniques in the code later on in order to smooth and reduce any noise on this input signal as well. So I'll show more about that later. And here's one of the output meters I'm using. So you can see on the back it's got 2 contacts here. These ones here, these are just screws to mount it to a faceplate. And what happens is when you apply the correct voltage across these 2 pins here, the needle rises from 0 all the way to the right hand side, and when you reduce the voltage it falls again. So there's a couple of things to note about this as well. So the first thing is that Arduinos, just like the fact that they don't really like dealing with analog inputs, they also don't deal with analog outputs. When you have one of the GPIO pins here, if you were to do a digital write high to it, for example, then it would set the voltage at that pin to 5 volts. And if you were to set a digital write low, it would set it to 0 volts. Now, let's just suppose for a minute that they correspond to 0 and 5 volts at either end of my meter here. Well, how then do we set it to some point in between? And the answer is that we basically turn that voltage on and off very quickly. So this is something called pulse width modulation. We don't actually change the voltage that we send out of the pins here, but what we do is we change the pattern of turning that voltage on and off. So let's say we're using pin 3, for example, and that is plugged in here, and the other contact is plugged into ground. So if we just turn pin 3 on, that would set this to 5 volts, and let's just assume that moves the needle all the way to the right hand side. And then we turn pin 3 off again, we now have no current flowing through here, and it falls back to 0 again. And then we do that quickly a few times. We go on, off, on, off, on, off, and the needle is quickly rising and falling. And if we do it quickly enough, what we find is that the needle basically doesn't have time to rise and fall in between each flick, and it will end up being in the middle. And in essence, that's exactly how pulse width modulation works. We will end up with an average voltage of 2.5 volts by turning our signal on and off, and so long as the amount of time that it is on at 5 volts for is equal to the amount of time it's off at 0 volts, the value being read by a meter like this will be 2.5 volts. If we wanted to increase it slightly, what we could do is we could say, well, let's turn the high voltage on and we'll leave it for, I don't know, 4 seconds, then we'll turn it off for 1, and then back on for 4, and then off for 1, and back on for 4. Well, that will give a voltage of 4/5 of 5 volts, which will take it to 4 volts on 0.8. Obviously, you wouldn't actually do it for a second. What we're talking about is doing this thousands and thousands of times every second. And because it's happening so quickly, you don't really see the meter flicking at all. It stays constant. This is the same way that we're able to dim LEDs as well. What you're doing when you're dimming an LED, you're actually turning it on and off very quickly, and to make it less bright we spend more amount of time in the off phase than we do in the on phase, and that's called pulse width modulation, or PWM. We have got one other problem to address as well, which is that you may have noticed that this gauge here is labelled MA, which is for milliamps. Now, I said that we were adjusting the voltage, which we are. We're sending a 5-volt signal, we're turning it on and off quickly to make an average voltage somewhere between 0 and 5. But this appears to say milliamps, which is surely measuring current. And sure enough, this is an ammeter, which is a current meter. Now you might be asking, well, hang on a minute, don't we want to have a voltmeter instead that's going to express volts between 0 and 5? And the answer to that question is, essentially, they are exactly the same thing. An ammeter and a voltmeter, one measures current and one measures voltage. But because current and voltage are related through the formula V equals IR, we can actually use them interchangeably. The only thing we need to get right is the resistance, which is the other part of that formula. So V equals IR, therefore I is equal to V divided by R. Now we know that V is going to be somewhere in the range of 0 to 5 because that's what the output of the Arduino is. And what I've got here is something that can display a current that is somewhere between 0 and 1 milliamp. Milliamp is 1,000th of an amp. So in order to get a voltage of 0 to 5 into a current of 0 to 1,000th, what I need to do is divide by 5,000. And to do that, all I need to do is to insert a 5 kilo ohm resistor in the signal line between the Arduino and the meter here. So if this was a 5 volt meter, or if this is a 1 milliamp meter with a 5 kilo ohm resistor in series with it, that's literally exactly the same thing. Okay, and having established that, what I can now point out is that you can actually remove the back panel here and replace this screen here, this kind of graphic, with anything you want instead. I've left the milliamp displays in here for now, but maybe you want to have some kind of suitable theme for your game instead that actually has some more interesting values on that. The last thing to mention on this point though, actually, I should have said this earlier, is that only some pins on the Arduino are capable of doing that PWM operation of switching on and off very quickly to alter their voltage. And again, on an Arduino Uno, the ones that can do that are the ones that have this little squiggle written in front of them. So we've got the pins 3, 5, 6, 9, 10 and 11. You can see it says here are digital PWM pins. So long as you're using any of those pins there, you can use the analog write function and specify the cycle, the amount of time that you want them to be on and the amount of time you want them to be off for. And what that will do is that will correspond to an average voltage somewhere between 0 and 5. That voltage, after it is connected in series with a 5 kilo ohm resistor, corresponds to a current somewhere between 0 and 1 milliamp, and that's going to enable us to position the needle exactly where we want to on our ammeter. So looking at the back of the board here, I just wanted to talk a little bit about how things are wired together. And I appreciate that's a little bit hard to see from this view here, so I'll show you a wiring diagram in a moment anyway. But I actually wanted to show you the physical layout of how the components are arranged and how the wires are running between them. Because when you're dealing with analog inputs and outputs, that actually becomes much more important than in a purely digital circuit. So obviously there's always some things that are important, like making sure you've got really good connections. I'm using screw terminals on a shield here to plug in all of the meters and the inputs as well. And I've soldered my resistors here. These are the resistors that are in series to the meters. I've also got some lines here connecting to the inputs. And a lot of these components have the need to be connected to ground on the Arduino. So we have 4 grounds to all the 4 inputs here. All of the LEDs need to go to ground. all of the meters need to go to ground as well. So that's 12 ground connections. So we've also got the relay that's on the front of the board here. Now I could have used, for example, a Wago connector like this one. This is actually the biggest one I've got, and even that's only got 8 inputs. So I would possibly have to have 2 of those connected together, and then one wire going to the Arduino and then splitting it out. And the thing is that having a common ground between all these components becomes really important in an analog circuit, because remember, we're measuring how far the slider has moved up the potentiometer as the ratio between the ground point and VCC. So if we haven't got an absolutely stable ground point to measure, all these inputs are going to be wrong, and also all of the outputs that we're displaying on the meters are going to be wrong as well. So what I've actually used instead is, you can see I've got a copper strip going along the middle of the board here. It's quite a wide copper strip, and this is my ground strip, and I've soldered all of the ground lines. So from the LEDs, they've got resistors going to ground here, and I've soldered these ones here, and then this one at the end, this is going to the ground on the Arduino. I've actually got a separate ground going to the front here, and that's going to make sure that the kind of the 0 point from which all of these inputs and outputs are calibrated is absolutely shared. This second copper strip at the bottom, well, this has got my 5-volt line, which I'm using for the analog reference. So all of the VCCs from the potentiometers, well, they're soldered onto this 5-volt line, and that's going to a ref on the Arduino. I've also got a little capacitor here. This is a 0.1 millifarad capacitor between ground and the a ref line, and that's just going to help reduce any ripples that there might be, to keep this a nice stable 5 volts, so that the input readings here are going to be more reliable. Now, in terms of the way that the wires are run as well, this is not as neat as it could be, but I want you to remember that these signal lines here, so these are what's carrying our PWM signals, our flickering on and off signals from our PWM pins here, that's going to turn the meter to a particular point. And the problem is, because these have got a signal on them that's very rapidly turning on and off, that can actually induce a current in other nearby cables. So I'm being very careful to run these cables around and across the top of the board here, far away from the input lines that I've got going to the potentiometers here, because if they were actually running side by side, what you'd find is that the PWM, the oscillating of that signal on and off, would actually cause the readings on the input signal to have that kind of oscillating noise in it as well. So you want to have a really clear ground and separate any signals that might potentially kind of induce noise. Keep them very separate from your input signals that you want to keep nice and clean. So here's the circuit laid out in fritzing, and there's not a whole lot more to add, but hopefully this might make it a bit clearer which pins are connected to the different components. So at the bottom here, this is where I've got my analog inputs from the potentiometers, and as I mentioned, I'm only using the A output of each of these, and they are going to analog in pins on the Arduino A0, A1, A2 and A3. And then I have the VCC pin on each of them. Well, that's connected to the A ref on the Arduino here, and I've got the grounds all connected together to the ground on the Arduino, and also to the common ground on all the other components as well. Over here I've got a small ceramic capacitor between the A ref and the ground line. That's not essential, but as I mentioned, what it helps to do is it just kind of steadies out the signal that you'll get on that A ref. It will stop any kind of small ripples that you might get, and you'll find it will just make the readings you get from these inputs a little bit more stable. So that's another tip, as well as keeping them physically separate from the other devices. We just put that on the line there. Over this side we've got a 5-volt relay, so that is connected to the 5-volt output of the Arduino, also to common ground, and then it is switched by an input on this signal pin here. so that's GPIO pin 2. And then we have our ammeters at the top. So these are connected to these PWM enabled pins. So I'm using pins 3, pins 9, pin 10 and pin 11. And you can see they've all got that squiggle in front of them to show that it's capable of producing that PWM signal. Now they go through a series resistor. Now I did say in the video a moment ago, so I said a ammeter that measures between 0 and 1 milliamp is the same as a voltmeter that measures between 0 and 5 volts with a 5 kilo ohm resistance. So the thing I noticed though is that the meters themselves do have some resistance themselves. So I haven't put a 5 kilo ohm resistor here, I've actually put a 4.7 kilo ohm resistor. So when that's put in series with the data line here, added to the resistance within the unit itself, what I found is that that enabled me to get the full deflection of the needle from the left hand side to the right hand side when I wrote the full range of values to these pins here. So you want the total resistance in this part of the circuit to be 5 kilo ohms, and I get that by adding 4.7 to the meters here. So you might need to tweak that value a little bit, but that worked pretty well for me. And then over this side we've got my 4 LEDs. As always, those are wired through a current limiting resistor. I'm using 220 ohms, and they are just connected basically to any spare GPIO pins I had. So I'm using pins 4, 5, 6 and 7. They weren't being used for anything else. And that is it. So here's the code that's running on the Arduino. Now in my last video I had a few comments that said that the font I was using was a bit small, so I've magnified it and hopefully you'll find it easier to read the text in this video. Thankfully the code listing itself is pretty short and quite straightforward. We're not using any external libraries at all, so all of the logic is purely contained within this one file. So we start off with some constants, and we declare the pins that each of our components are plugged into, so the ones which I just showed you in the wiring diagram. Our ammeters are plugged into GPIO pins 11, 10, 9, 3. The input potentiometers are in the analog pins 0, 1, 2, 3. Then we've got the LED pins and the relay pin. Now for this particular example I have got 4 inputs and I've also got 4 outputs, but that doesn't actually need to be the case. You can add as many elements into these arrays as you want, and you don't have to have a matching number of inputs and outputs because there's not a direct one-to-one correlation between them. That's what makes the puzzle interesting. So if you want to change these numbers around and add different inputs and outputs, that's fine. You can do that really easily. We then define some target values. Now I need to explain this a little bit. So we've got input values that are read from the ADC, and I mentioned that that was a 10-bit converter, so we get numbers in the range from 0 to 1023 on the input. But when we go to the output side of things, the PWM that we output, well, that's 8-bit resolution. So we can set one of 256 different values on that variable voltage that we output from the PWM pins that goes to the meters. So what I've defined here is what one of those values do we want to correspond to the solution to the puzzle. So if it's an 8-bit value that ranges from 0 to 255, and we want the solution to be the point at which all of the meters are in the midway point, that would be 128, because that is halfway between 0 and 255. If you wanted to make it so that the puzzle required players to have all of the meters all the way over the right, for example, you would change the target values here to be 255 instead. Or if you wanted them to be a quarter of the way, it would be 64, whatever it is. So just think in fractions of 255, because that PWM output is an 8-bit value. So just to explain why we're getting those numbers there from. So what this means here is that the puzzle is going to be solved when all of the meters are pointing right in the middle, straight up. Now, another thing to bear in mind about when dealing with analog puzzles is that you need to have a sort of a bit of leeway, a bit of tolerance either side of the correct answer. Because, as I mentioned, unlike a button that's either pressed or not pressed, with an analog input you've got a whole range of values, and you kind of think, well, is that close enough to be considered the correct answer? So that's what this tolerance here is for. Although the ideal answer is going to be 128 out of 255, we'll actually accept any output value that's 5 either side of that. So if you want to be kind of more generous in what you allow players to input, if you want to make it an easier, as it were, you would increase this value. If you want players to be really, really precise, you could take this down to a low value. But I would recommend not having it at 0, simply because of all those issues I mentioned about noise and getting the scale exactly right and things like that. You'll probably end up frustrating your players if they have to get the exact value. So I found 5 was a good number for me, but you can fiddle with that if you want. So those are all constants. Those are not going to change throughout the duration of the script. And then we've got some global variables as well. So these are values that could change. And what we've got is we've got an array of input values. So this is going to be the raw value that we take from the ADC of each of the potentiometer inputs. As I said, that's going to be in the range 0 to 1023. And then we have the array of output values as well. Those are going to be 8-bit values that are in the range 0 to 255. And we'll also have a Boolean flag to say, well, has the puzzle been solved or not? And that's what we're going to use to decide whether to activate the relay or not. And that's going to be responsible for opening the maglock or turning a light on, or whatever it is that you want to then go on to the next stage of the game once this puzzle has been solved. So then we go on to the setup function. So the setup function gets executed once when the script first starts, when the Arduino is first powered up. And so this is a habit which I've now got into in all my recent projects basically. I start a serial connection, so that enables the Arduino to print messages over the USB cable that's connected to a PC. So if you've got the Arduino IDE running and you connect it to the device, this will start a serial connection. And then the first thing I do is just print out the name of this file, so it's called Analog Puzzle, and the date at which it was last compiled and sent to the device. Because I've got a whole ton of different Arduinos and other processors as well, and they're all running different scripts and different versions of those scripts, and it's really easy to lose track of what device is running what. So if you include this at the top of your script each time, if you ever find an Arduino lying on the floor, as I often do, what you can do is you can pick it up, plug it into your PC, start the Arduino IDE monitor, and it will tell you what the name of the script that Arduino is running. So that's kind of useful. We'll initialize the pins. So we've got an array of 4 meters, which are outputs. We've also got an array of 4 LEDs, which are outputs, and the relay pin is an output. We don't need to define the slider pins as inputs because input is the default state anyway. So when we come to do an analog reading of these pins, they'll already be in the correct state. And we write a high signal to the relay pin because, as I mentioned, my relay is an active low relay. So its default state basically is to have a high signal written to it. And then if we write a low signal instead, and that's what we'll do when the puzzle is solved, when all of the meters are pointing at the values that we write here. And the low signal will cause the internal sort of switch to flip across from the normally closed to the normally open. So what was normally closed will become open, and what was normally open will become closed when we write a low signal to it later. Okay, and then we get on to the loop function. So the loop is the main program loop that just goes over and over and over again for as long as the Arduino is powered up. And we go through a sort of a series of steps one at a time, and you can see I've kind of put little headers here as to what we're doing at each stage. Some people, when they code, they would prefer to kind of separate out this function into a separate section here that you then call from the loop function. And certainly if you're dealing with like a large complex project, that's quite useful to separate out all of your sections of code into different functions. But actually, for something that's relatively straightforward, I think it's easier to read when you just write it all in line in the loop function. So, you know, that's code preference, but for me this makes it easier. So the very first thing we do, every time we go through the loop function, the first thing we need to do is, well, we need to find out what the current position is of each of the sliders. And that's what we're going to do here. So we'll loop over all 4 sliders. And what you might think we could do is just use the analog read function to take a reading of what the current value is. But there is a problem, and I mentioned this earlier as well. So an Arduino Uno has 6 analog pins, or pins that can be used to read an analog voltage input. And an Arduino Nano has 8 of them as well. But the 80 mega chip that they use only has a single analog-to-digital converter. And the way that the converter actually works is it's basically a little capacitor. And it charges up the capacitor using the voltage that's being provided on the analog pin that you're trying to take a reading of. And then it times how long it takes to discharge that capacitor. So, you know, obviously you're supplying a higher voltage at the pin, it's going to take longer to discharge, and it can use that to calculate how much voltage was being applied. That's all fine. And when you take an analog reading of several pins, one after another, which is what we're doing in this loop here, we're looping over all the pins and reading one after another. What can happen though is effectively the ADC chip retains some of the charge, some of the capacitance that it had from the last reading. It's not starting at 0 every time. And this is a problem if you're trying to read many different analog pins in quick succession. So effectively what we need to do is we need to discharge the ADC before we take a new reading, just to make sure that we're going to get an accurate reading of the analog pin we want. And the way we do this is effectively to take a couple of kind of sample readings and throw them away, because the very act of taking a reading from the ADC will actually help discharge any residual capacitance it's got. So we loop over the pins, but then rather than taking a reading straight away, we go into this loop here first and we take a reading of the pin, but we don't do anything with it. We're not assigning this to a variable at all, we're just taking a reading, and then we're waiting 5 milliseconds, and then we'll take another reading, and then we'll wait 5 seconds. We don't do anything with that. And then finally we take one more reading, and this time it's the one that we will use and assign to the input values array. So this is one of the ways you can use to improve the quality of your analog data. We talked about making sure you have a good ground. We've talked about making sure that the signals lines are physically separated, and this is a software technique you can use to get a better quality analog reading, is by just throwing away a couple of readings each time. And this really doesn't delay the code by very long, because we're only talking about 5 milliseconds that we're doing this loop for here, and we're doing it twice. So you won't notice hardly any lag at all, but you'll get a better result afterwards. Okay, so our input values array now has got 4 values in it, because we did this 4 times, that hopefully are clean signals somewhere in the scale of 0 to 1023 that represent our inputs. So now, this is where the magic happens. This is effectively the game logic that says how those output signals, what those meter values displayed are, how do they relate to what the inputs are. And you can use your imagination here to kind of create any rules you want. I've just literally put in 4 different quite simple rules which I thought would create interesting responses. So the first meter on the left hand side, well, that shows the maximum of the first and the third sliders. So if you remember back to the beginning of this video, when I first moved the left-hand slider up, that made the left-hand meter go up. And what players would probably assume at that point in time is that they were directly related. And they are, but it's also directly related to whatever the third slider was. And at that point in time, the third slider was at 0, so you wouldn't have noticed it had any effect. The second meter along, well, that one I've got to have the difference between the second slider and the last slider. And it's the absolute value of the difference. So ABS is one of the built-in math functions. That means ignore the sign of a value. So don't worry whether it's negative or positive. Just give me the amount of the value. So we're going to work out what's the difference between the second slider and the fourth slider. And we'll set that to be the output value of the second meter along. So again, when players were doing this right at the beginning of the game, the slider at the end was set to 0. So when they start moving the second slider along and it appears to affect the second meter directly, their assumption is that those two are directly correlated and they don't think that this one has any value. That's what I think makes this puzzle quite fun, because you know, we're used to reading from left to right. Certainly in most countries of the world, we read from left to right. We naturally scan across a set of controls in that direction as well. So when we see a set of levers, people often attempt to move the first lever on the left-hand side, assuming it's going to move the meter on the left-hand side. And it does to start with, but that's kind of coincidence, really. Then we get to the third output. Well, that now we're looking at the average of two different meters. Again, at this point in time, this slider, has not moved at all, and that's why it seemed that I had to move the slider twice as far up to actually get the meter to move halfway, because it's being averaged with a value of 0 at that point in time. And then finally we get to the last one. Well, that's a minimum value, so that's much like the maximum value that we had the first time, but this was set to the value of whichever one of these two inputs is less. So you can do all kinds of fun things here. You can add two inputs together. You can have a dummy input that actually has no effect on the output at all and things like that. You can make it as simple or as complicated as you want. But it's quite fun to have, to play some tricks on your players and to make them believe that there is a pattern that they've discovered, and actually it's not quite the pattern they thought it did. But it does need to be logical. You know, don't just put in a random number generator here or something like that, because the players need to get the satisfaction of figuring out what these rules are experimentally, by observing different inputs and the outputs they lead to. So yeah, you can do what you want, but that's just some example values which I put in there. And if you go back to the beginning of the video and watch my example, hopefully you'll be able to figure out how those rules worked. Okay, so we've now got an array of output values, we've got an array of input values. What do we have to do them now? Well, now we have to convert them into the correct scale to send to that PWM output. So at this point in time, the input values are in the range 0 to 1023. Sorry, I've got a comment here that's wrong. Actually, let me get that out because that's not true anymore. At one point I rescaled this down to 0 to 100, which I thought would make it easier to work with, but actually I've decided to scrap that, so ignore that bit. So we've got input values that are 10-bit, we've got output values that are at the moment directly based on the input values, so they are also in the range 0 to 1023, but we need to convert them into the 8-bit range that we can send to the PWM. We also need to check whether they're the correct value or not for the output. So what we do here is we set up another flag, and we're going to call this all meters correct. Now I'm going to assume that this is true, and this is kind of a common technique which I use. When you've got a whole range of inputs and you want to make sure that they're all right, you might kind of instinctively think, well, the way to do that is to assume that they're all wrong to start with,
and then loop over all of them, and if they're all correct, then change it to correct instead. But from a programming point of view, it's actually easier to set up that test the other way round. What you do is you assume that they are all correct to start with, and then you loop over them in turn, and as soon as you get to any one of the values not being in the correct position, so as soon as any of the meters are not pointing at the correct target value, you know from that point onwards then they can't all be correct. Because basically any not correct is the same as all not correct kind of thing. Does that make sense? I hope so. So it might feel like I've set that up the wrong way around, but that actually is a more efficient way to test, really. So we'll assume they're all correct, and we'll loop over them all. And the first thing we need to do is to rescale them. So like I said, instead of being from 0 to 1023, we want to scale them from 0 to 255. Now, I started off by putting the full range of both values there, but I found that with my meters, I don't know if it's just the particular style of meter I have, or whether they're not hugely accurate on the scale or not, but I found out that they were never quite hitting the top end of the scale when I did that. Maybe my resistor value is also a bit too high, I'm not sure. So I just moved this down slightly to 1010. So what this means is that the inputs from 0 to 1010 are going to go to 0 to 255, and if there are any inputs greater than that, so in this tiny bit of range of input at the top, they're going to actually go off the end of the scale here. So then I do the constrain function here. This is going to make sure that the end results lie in 0 to 255. So I'm going to map the outputs into the correct scale to start with. I've brought the end down slightly, so this is just going to make sure that I do match the full extent of the scale. And again, this is a number that you might need to tweak depending on the exact meters you're using and things like that. In theory, that should work if you have the exact resistance right, but I found that number worked better for me. So now the output values lie in the correct range for PWM, and we can use the analog write function to actually make the pin needle, the needle on the meter point to the correct output values. And then we need to test whether the puzzle has been solved or not. So once again, we'll use the absolute function here. We'll compare the absolute difference between the output that's being shown on the meter and the target value that we defined right at the top of our code again. So remember, our target values that I'm using here is 128 in every meter, so that's halfway. And if the absolute difference between the value that it's actually showing and that target value is greater than the allowed tolerance, so our allowed tolerance was, I think, 5. So if it is outside of 5 either side, well, that means it's not correct. So we can set our flag here, all meters are correct is not true, because there is at least one that is outside that tolerance. And we will turn the LED off corresponding to this meter. If the absolute difference between the output value that's been calculated and the target values is less than the tolerance, however, that means that this meter is in the right position, and we'll turn its LED on instead. So we do that for all of the individual output values, and then we get to this point here. Now, if we've got this far and all meters correct is still true, that means that this section of code here was never called, and that means that all of the individual output values must have been within their tolerance. So if that's the case, and if the puzzle wasn't solved before, that means that we have just got the final meter into its correct position. We've just solved the puzzle. And so here you can add code to do whatever you want to do when the puzzle is solved. I'm going to write a simple message onto the serial monitor. I'm going to set the isSolved flag as true, so that we know that on the next iteration through the loop the puzzle was in the solved state. And this is where I'm going to activate the relay as well, so this is going to be able to power whatever you want to happen when the puzzle is solved. The opposite of this is if the puzzle previously had been solved, so if on the last time through this loop, if the puzzle had been solved, but now it's not the case that all the meters are correct. Well, in that case, we were in a position at the right solution, and what's happened is the players have now changed one of the input values, so it's no longer solved. So in that case, we're going to do the opposite. We're going to say it's now unsolved. We'll set the isSolved flag to false, and we will set our relay to high, and we'll relock the maglock or whatever it is that we might have done in that case. And then finally, we'll just do a little bit of debugging output. So I find that this is always useful whenever you've got a bit of code and if you're not quite getting it to work the way that you think it's going to. And this is, incidentally, this is how I came up with the value that I had here. So I was looking at my inputs and my outputs that I was getting, and I was trying to make sure that, you know, when I went from the very bottom of the potentiometer to the very top, that my needle for the corresponding ammeter was going right from the very left to the very right. And the way I did that was to plot them on the Arduino serial monitor. In the serial plotter. So the serial monitor is like a kind of a tabular output that just gives you text, but the serial plotter gives you a graph of different values that you print to it, and that's a really useful way for looking at analog values as well. So that's just what it does here. And then finally, we'll just put in a short delay, just 50,000th of a second, and then we go through the whole loop function again, and that just continues to run over and over.
So that just about brings me to the end of this tutorial. I hope you enjoyed watching the video and that you were able to find something interesting or useful about dealing with these kind of analog inputs and outputs. Like I say, they're not particularly complicated, and I think they do open up a whole new possible way of interacting with players and puzzles and escape room games. But there are just a few things to watch out for, and hopefully I was able to communicate what those were. As always, I will upload the code that I'm using together with the wiring diagram and list of parts and things like that. I'll put that over on my Patreon page, where you can also find the downloads that go with all of my other escape room projects that I put up in this channel. I'm only able to make these videos with the support of my Patreon donors, so I want to say all thank you ever so much for your continuing support. You're all amazing. I do really enjoy making these videos, but they take a surprising amount of time to research and create, and I'm only able to do that with your support, so thank you all very much. If you are able to support me, do head over to Patreon to see how. If you are not able, or if you don't want to, that's fine as well. I will just keep on putting these videos up on YouTube for as long as I'm able to. If you have any comments or suggestions or questions about this project, please do let me know, and I will do my best to answer them. But otherwise, I will look forward to seeing you next time. So thank you all very much for watching. Okay, cheers, bye-bye.